is it visible now? Hello? Is it okay now? Hello? Anyone respond, please?
Yes, sir.
Sir, visible, sir. Sorry for the interruption. There is a network problem. So, now we are calculating the coding redundancy with the help of compression ratio and average L average. Okay, but code word is different. Code word length. First code word is fixed code word. Second code word is variable code word. The example for variable code word is Huffman code. So this Huffman code is having different bits, variable bits. So in the third column, this is the last but one column. Okay, using this formula, we are calculating how many how many calculations we will get? 8. So if you sum all these 8 values, after the summing of all the 8 values, you will get 2.7 bits, approximately 3 bits. So rounded to 3 bits, of course. So after getting your L average, what is the CR? CR is compression ratio is given by, what is compression ratio? For each one, input image is N1 and output image compression is 2.7. So if your input is 3 bit and output is 2.7, you will get 1.11. So about 10% is only reduced. So the image can be reduced to up to 10%. So the total number of bits compressed in the image is, or the size is, how much it is? L average into NM. So 2.7 into NM. And redundancy. What is redundancy now? Your total redundancy is given by 1 minus 1 by 1.11. So this is the amount of redundancy. This is the amount of redundancy is happened or can be calculated using the code word or Huffman code, a second type of variable code word. Okay, the first case, how much you are getting? Here 3 bits, and total number of bits are 3 into NM. But using variable code word, that is Huffman code word, what is the total number of bits? All of you, please take, all of you can write this table. It's very easy. All of you take case 2, case 1 and case 2. What is case 1? In case 1, we are considering only a fixed code word, right? In second code word, in second case, we are considering code word 2. Just we add code word 2 to the previous table only, and with it, different bit lengths. And from this table, we are calculating total number of L average and total number of bits or the size of the image for this variable code word. So, 2.7 N, right? Please take all of you. Note down. R not equal to 0, R1 equal to 1 by 7, R2 equal to 2 by 7, R3 equal to 3 by 7, R4 equals to 4 by 7, R5 equals to 5 by 7, R6 equals to 6 by 7, R7 equals to 1. These are my levels. And what is probability? The probability is PR of RK, second column, and 0.19, 0.25, 0.21, 0.16, 0.08, 0.06, 0.03, 0.02. Next, for these corresponding levels, what is code 1? Code 1 is very simple. Fixed code word length 000, 001, 010, 011, 100, 101, 110, 111. And L1 of R suffix K, that is L of R suffix K, simply. L of R suffix K. So what are the bit length? All are equal bits. 3 bits, 3 bits, 3 bits. Next, code 2. this code 2 is I'm considering here first R level. R not 1 is having, or suppose 2 bits, that is 1 1 0 1 1 0. This is our this is our requirement. Depends upon our requirement, we will vary 1 1 0 1 1 0 triple 0 1 double 0 1 triple 0 1. Remember, this code is we will calculate it, later on. Uh, uh, we will calculate this coding. We will find the coding in the preceding the further classes. We will calculate Huffman code. I will show the example. Okay, just for example, we consider here 1 1 0 1 1 0 0 0 1 triple 0 1 double 0 double 0 1 triple 0 double 0 1, all zeros, last, and L2 of R suffix k, that is second code. Bit length of second code is given by 2 2 2 3 4 5 6 6. Okay, so from this second code word or Huffman code variable length code, calculate L average with number of levels or average of bit length of average. uh, you will get 2.7 bits. 2.7 bits. Row number 13, please mute yourself. Okay. So from this total number of bits is equal to sorry, L average. We will, if you sum all these 2.7, you will get 2.7. So from this CR and our correspondingly RD calculate. Just note down. Okay. Next, total number of bits is 2.7 NN. So previous one NN using code word to 2.7 N. So there is a change in 0.3. 0.3 size will be reduced. Next, interpixel redundancy. Interpixel redundancy is interpixel redundancy. What is interpixel redundancy here? So interpixel redundancy is just editing interpixel redundancy. So in interpixel redundancy, which implies that pixel values are correlated, not bits, or there is no manipulation in the bits. So instead of bits, we are manipulating pixels, right? Not bits. Only pixel values are manipulated, that is correlated, and a pixel value can be reasonably predicted by its neighbors. That means, as like in our previous units, that means filtering of spatial filtering and frequency filtering. That means in spatial filtering, what actually in the spatial filtering, we are manipulating the pixel values for the intensity, the resolution, or the histogram purpose. We are manipulating the, or we are interchanging the pixel values from one place to another place. Okay, are predicting the values by its neighbors. So like this here also, there is an histogram and autocorrelations. For this, we are having, there is a function. There are two functions, f of x and g of x. F of x over g of x, which indicating the autocorrelation, is given by integration of minus infinity to plus infinity to f of x into g of x plus a into dA. So here autocorrelation is given by f of x equals to g of x. Okay, and this in this interpixel redundancy, uh, those who are having same values of intensity values or can be reduced or can be eliminated for the reduction of, or the for reduce this size of your image. And here, if we observe histogram values before and after compression, before and after them. There are two images and their grayscale histograms and normalized autocorrelations like this. Interpixel redundancy. Just write the statement. Interpixel redundancy is implies that pixel values are correlated. Pixel values are correlated. That is, the pixel value can be reasonably predicted by its neighbors. So don't consider and don't consider the value if the neighbor value is same as that of both are have same value. Don't consider the next one. So based on the neighbor value, we can predict or we can expect or we can estimate the present value of or the present pixel value without considering that particular pixel value. Next. So to reduce the interpixel redundancy, some kind of transformation must be applied on the data. So here, like this, there is a original and this is a binary image. Original image and binary image. So the transformation technique already we have completed in our previous units, previous chapters. For suppose what is the threshold value for this one C04? This is an image. This is original image, and converting it to the binary image. And if you manipulate using run length coding, what is run length coding? So additional saving bits run length coding is threshold value is for suppose if you set one threshold value at 195, okay, 195, and uh, 70 71 suppose 751 to and another threshold value is 751 to 8813 and correspondingly 1023. So here using the run length coding and using 11 bits per pair and of course run length coding is also we will explain in the previous section. Just consider uh, 1 comma 63 0 comma 87 and 1 comma 37 0 comma 5 1 comma 4 and 0 comma 5 comma 556 and 1 comma 62 comma 0 comma 210. So like this if you consider using 11 bits per pair, for suppose for this 1 comma 63 there is a pair, and if you use 11 bits per pair and the total bits are divided into 1 plus 10, that is first bit is in all the pairs there is a single digit. So for all the single digit if you use 1 plus 10, that is 11 bits per pair, and we will require how many bits? 88 bits per 88 bits are required or compared to 1024. So instead of 1024 we are getting or we are requiring only 88 bits for image. Wait for 1 minute. So sorry for interruption. Next, psychovisual redundancy. So in psychovisual redundancy, the human eye is more sensitive. Already I told you the psychovisual redundancy due to some psychological or due to some different eye perceptions, we are observing more than one or more frequencies instead of one frequencies we are observing. So that is the human eye is more sensitive to the lower frequencies than to the higher frequencies in the visual perspective. So that means for high frequencies the human eye is less sensitive, but for low frequencies it is more sensitive. So then based on the frequency of an image, that is there is an idea and which is discard data that is perceptually insignificant. So if you observe here, I'm changing the grayscale levels from 256 16 and 16 grayscale levels plus random noise. So in the first case, quantization in 256 level grayscale levels, the image is different. In 16 grayscale levels, the image is different. And the second one is original image along with random noise. Okay, so add some pseudo random noises to pixel values, and we are observing the C equals to 8 by 4 or 2 is to 1. 8 by 4 or 2 is to 1 based on this compression ratio. So 8 by 4, that means 2 is to 1 ratio. The psycho-visual redundancy is the I is your human high is low, very low sensitive for higher frequencies and more sensitive for lower frequencies. So here I am measuring information. So the key question in this image compression is, first of all, what is the minimum amount of data that is sufficient to describe completely an image without loss of information? This is our actual main concentration on the image prediction or image preserving of our original image without losing the information. But the compression is also very important. That is already I told you there is a trade-off between compression and loss of information. So due to there are two techniques, lossy compression techniques and lossless compression techniques. Based on your requirement, choose yourself which one is suit for your application, either lossy or lossless. So in lossless compression, information may be preserved, but compression ratio is very less. But in the lossy compression techniques, information may be lost somewhat, but compression is more, right? So based on that trade-off, here we require one statement, that is, what is the minimum amount of data that is sufficient to describe completely an image without loss of information. The statement is very important while compressing the an image. So how do we measure the information content of an image? So there is some information information content is measured by some expected values, entropy, like this. And there are some information generation is probabilistic process and associated information with probability. So write this, all of you. Measuring information. How we are measuring information? First, we have to assume that information generation is a probabilistic process, not a fixed. It is a probabilistic process. Right, all of you. Measuring information is, the first point is, we assume that information generation is a probabilistic process, not a fixed process. And second one is associate information with probability. Every information is having some probability. And now we require some expected value that is called represented with E, and it is definitely a random event E with the probability P of E contains like this. So we are treating as capital I of E, which is indicating what is capital I? Capital I indicating information, and E is an event or the expected value. An event or an expected value, and which is given by capital E of E is given by log of logarithmic of 1 by P of E. So what is P of E is here? Probability of an event or probability of an information. Right? If you know the probability of that an event, calculate log of 1 by P of E, and you will get minus log of P of E, of course. And there are some units of information, and is given by one more thing, the maximum limits, or the, if capital I of E equal to 0, then P of E equals to 1. If the probability of expected value is 1, and your information of expected value is definitely 0. Okay, so by knowing the information the probabilities of informations, we will calculate the P of E, and from that P of E calculate I of E, right? So don't confuse here. Simply E is an event with that information is generated. E is an event, and of course with having some probability P of E, and with that probability the information can be generated. Information generation. So simply information generation is not a fixed process, it is a probabilistic process. All of you remember, it's not a fixed, it is a probabilistic process. And the probability can be calculated using this formula: I of E equals to log of 1 by P of E. So just note down the expression: I of E equals to log of 1 by P of E equals to minus log of P of E. Next, how much information does a pixel value contains? So now the amount of information is having a pixel value is calculated with the same, that is I of R of k, which is indicating I of R of k is, what is the R of k? It is intensity level and pixel value for a particular intensity level. RK is indicating a particular intensity level. So in that intensity level, what is the information is given by minus log of P of R of k. If you know R of k value, that means R0, R1, R2, R3, small R1, R2, R3. So if you consider 8 levels, how many levels? 8 levels. So that means R0 to R7. So for corresponding those intensity levels, the corresponding information is having I of R suffix k. So assuming statistically it is an independent random variable, and it is must be not a fixed value. So that means the intensity values are changes from one value to the another value. Over an image, let us consider, and if you look at some points, so all points are definitely not equals to equal intensities. So while you are changing the distance, while you are changing the position, the intensity values are also changes. So that means the levels are changes from R0 to R7 or R0 to RL minus 1. So here L is your number of intensity levels depends upon your requirement. Suppose that the grayscale level values are generated by a random process, then R suffix k is definitely also a random variable. Like pixel value is random variable, the intensity level is also random variable. And from this randomness of your intensity level, we will calculate the intensity of or I of or the information of a particular intensity level is given by minus log of P of R of k. So if you know the probability of a particular intensity level, definitely we will calculate the information of that intensity level. That indicates what is the amount of or how much information is incorporated or having the intensity level. Here simply consider intensity level is a data. Intensity level is a data, not information. So already told you, information is different, data is different, but information is carried by your data only. So here consider intensity level is a data, and information is our requirement, which is carried by that intensity level. So if you want to identify, or if you want to know the how much of amount of information is incorporated or uh, incorporated in that intensity level or data, you use just simply this expression I of R suffix k equals to minus log of PR of RK. Just so with this expression, we will calculate an information of any intensity level or of any data. Next, the average information. So once you know the one intensity level or information of one intensity level, and let us consider there are 8 levels. So how we are getting the average information of an image? Just by summing all this information, as that is I of R of k. and it is given by E. Must remember, don't confuse. Here only one, here only one intensity level information. But in an image, definitely there may be not a single intensity level. Definitely there are a number of intensity levels or a number of grayscale levels. So based on those number of grayscale levels, for suppose I am considering here 8 intensity levels. 8 means k equal to 0 to L minus 1 means 8 minus 1, 7 minus 1 maybe. But generalizedly I am saying that here capital E equals to, that means it is represented with an average information, and which is equals to sigma k equal to 0 to L minus 1, and it is a product of information. That means information contains in that particular intensity level, and the probability of that particular intensity level. So if you calculate for single level, you will get one value, and second level you will get another value, and correspondingly there are 8 levels and 8 products. And if you sum all these values, you will get the total average information content in an image. So using this expected value, and also using the same intensity or the same information in the one single value, we will calculate entropy also. So what is entropy? This is E is called as average information, or also called as expected value, and there is another term is there that is called as entropy. So here entropy is given by H equals to minus minus uh, here remember one thing: units are bits. Units and bits both are equal. Units or bits both are equal. So we have to calculate entropy is given by simply minus sigma k equal to 0 to L minus 1 P of R of k into log of P of R of k. So what is P of R of k? This is a probability of a particular intensity level. What is log of PR of k? Already we are having here I of k. I of Rk. So simply the entropy is given by minus sigma k equal to 0 to L minus 1 I of Rk into what is it? P of Rk. Already we are getting I of Rk. So to get this I of R of k, we are using minus log of P of R of k. Same, if you use this, if you take the product of these two terms, you will get the entropy. So simply the entropy is given by H. So once you know the expected value and entropy, now let you take this please. Please note down E value and H value. E value and H value. Note down average information content of an image. E value and H value. Is it over? You want to previous one like this. Measuring information. Note down measuring information. I of E log of 1 by P of E equals to minus log of P of E. I of E equal to 0, then P of E equals to 1. Next, how much information in a pixel value contains? It is given by I of R k equals to minus log of P of R. Over. Over. So the units for I of RK is bits. Bits are units. Bits are units. Next, average information E. Average information E is given by E equals to sigma k equal to 0 to L minus 1 I of RK into P of RK. Entropy H. Entropy H. All of you know down. Entropy H is given by, entropy is generally bits per pixel value. Entropy is indicating the bits are units per pixel. E I H. E equals to sigma k equal to 0 to L minus 1 I of RK into P of RK. I of RK equals to minus log of P of RK. And H is given by minus sigma k equal to 0 to L minus 1 P of RK into log of P of RK. Over. Is it over? Next, redundancy. So what is redundancy? So redundancy is simply L average minus entropy. It is the subtraction of entropy from L average. So if you know L average, just subtract the entropy from that L average, you will get redundancy. So here, if L average equals to H, then redundancy is 0. There is no redundancy. Okay. Just write down redundancy. Redundancy is given by L average, that is number of symbols or number of bits per code word is minus average number of bits or average number of symbols per code word minus the entropy. You will get the redundancy. Okay. So, so just note down up to this enough. So in last class we will calculate estimation, entropy estimation. So up to now we have calculated redundancy with the help of L average and entropy. Entropy is represented with H. Entropy is represented with H. Okay. With this, I'm concluding today's topic. I have some work. There is an exam, lab examination for the engineers.